All right, so I'm the chair of the committee, and so Cena will give his presentation within the first hour, 45 minutes or so.
45 minutes.
Okay, and then so for the general audience, you can ask questions in that session. Then we'll ask you to leave, and you'll stay, and then we'll ask you more in-depth questions. If the committee has any questions, maybe we constrain them to clarifying questions if it's disrupting the flow of what you're saying. And I'd like to give a couple minutes for you to maybe introduce your student.
Yeah. Okay. Hello, everyone. So I'm very happy to have Sina graduating, hopefully today. So, well, Sina is setting a record, at least for as far as I know, is finishing his PhD in 3 years. And if you actually count the number of journals he has, I think like 7, 8 right now. So he has published a lot more than I have during my PhD, and fantastic work. I think what he's doing is groundbreaking in terms of the idea, and very excited for him to present his work. So, yeah.
All right, Sina, please.
Okay. Good afternoon, everyone. Thank you for being here today. I'm honored to present my PhD research entitled Configurable Multiport Radiators. This work has been conducted under the supervision of Professor Tusi, and also I would like to thank you all committee members for your time throughout this process. As you know, antenna play a critical role in wireless communication system as they convert electrical signal into electromagnetic radiation. However, most of the antenna used today have only one port. That poses some problem for wireless transmitters. This problem involves demand for increased radiated power, especially when we have access limited supply voltage. In traditional wireless transmitters, the output of multiple amplifiers can emerge at a single port of radiator using a passive power combining network. However, these networks are lossy and have limited frequency bandwidth. An effective method addressing this issue is using phased array antenna. This method aims to combine radiated field in far field without loss and enable beamforming as well. However, this approach has its challenges. Phased array are fundamentally limited by primary single port of radiator. This will restrict the bandwidth and also radiation patterns. This is exactly where the concept of multiport antennas comes into play. Multiport antenna offers a unique approach to an antenna power combining by passing the limitation of other method. In this method, the output of multiple amplifier can be directly connected to the surface of antenna, and making the multiport antenna a more compact and less lossy solution. However, designing a multiport antenna is difficult due to the complicated electromagnetic structure. The multiport idea has been applied to different types of antennas so far. However, current works on multiport antenna have certain limitations stemming from iterative numerical simulations and EM simulation. This imposes a significant burden to design a large-scale multiport structure. And that was our motivation to be focused on a theoretical studies and a systematic design procedure based on the theoretical study to remove needing EM simulation. This slide provides an overview of multiport or research on configurable multiport radiators. Our goal is to develop multiport antennas with adaptable features. And we do this process through two different approaches. In first one, we provide accurate theoretical analysis of the structure. And in second one, we just predict the radiation characteristic based on the parameters of some part of the antenna. In the first project, we provide a multiport wire antenna that can provide a one-dimensional configurable radiation and also adaptive filtering. In the second project, we extend our idea to a two-dimensional configurable radiation using a multiport patch antenna. But in the third project, we are focused on multiport periodic antenna, and we show the ability of two-dimensional configurable radiation just by using the S parameters of the unit cell. At first, I introduced wideband configurable one-dimensional wire antenna. The approach we follow in this work is calculating and manipulating the surface current distribution on the surface of the antenna. And based on this current distribution, we calculate the radiation pattern and impedance matrix. Predicting the radiation pattern enables us to do beamforming and beam scanning, and predicting the impedance matrix helps us to maximize the accepted power from each port. To analyze the multiport wire antenna, at first we calculated the surface current distribution based on the magnitude and phase of excitation and also location of each port. And then we used the EMF method to calculate the impedance matrix of a multiport wire antenna. Also, we derived the radiation pattern function based on the current distribution function. It is noticeable that the entire design process in this work is based on this function, and we never used EM simulation to design. Next, I will discuss the systematic design procedure. The proposed systematic design procedure starts with desired radiation pattern. Then we calculate the surface current distribution can generate this desired radiation pattern. Then we determine the location and port excitation can generate this current distribution. And finally, we calculate the phase and voltage of each sources based on the impedance matrix of multiport wire antenna and impedance sources. This flowchart illustrates the steps of systematic design procedure. Firstly, we select the ideal radiation pattern, center frequency, and length of the antenna based on the required beamwidth. Then we select initial value for location and excitation of each port. Then we calculate the radiation pattern based on this initial values, and then compare it with ideal radiation pattern. And we compare using the mean square error matrix. And based on this error value, we update the location and excitation of each port, and we do this process until obtaining minimum error. And then, if the obtained radiation pattern is sufficiently close to the desired radiation pattern, if it's not, we increase the number of ports and do this process until we arrive to the desired radiation pattern. And then finally, we evaluate for the accuracy of our design using the EM simulation. Let's see the result of this algorithm for a design example. In this example, the center frequency is 12 gigahertz, beamwidth is 20 degrees. Based on this required beamwidth, we select the length of 21 centimeter for the antenna. The normalized mean square error plot show that minimum error is obtained for 11 number of ports. And in radiation pattern plot, you can see that the synthesized one and simulated radiation pattern are in good agreement. And finally, we published this analytical study in IEEE Antenna and Wireless Propagation Letter. Next, I will discuss the prototype. Here you can see that the proposed multiport wire antenna based on last design example, which is realizable on the PCB and include the power divider network, the phase shifter stage, and finally the multiport radiator. And we fabricated and measured the prototype, as you can see in this picture. There is a comparison between the measurement and simulated input reflection coefficient for this case that, as you can see, antenna is well matched from 5 to 18 gigahertz. And this figure shows a comparison between the simulated and measured broadside radiation pattern for 4 different frequencies from 5 to 18 gigahertz. This demonstrates the ability of multiport wire antenna to synthesize radiation pattern across a wide frequency bandwidth, in contrast to typical phase array. And this figure demonstrates the ability of continuous beam scanning from backward to forward flow broadside radiation with less than 1 dB gain variation. This one is achieved at 15 gigahertz, which is also achievable in all the frequency bandwidths. This figure provides a comparison between peak gain obtained from theoretical model, simulation, and measurement. As you can see, the measured gain is approximately 1 dB less than simulated one, can be attributed to the measurement tolerance. This figure shows the efficiency of multiport wire antenna and also entire boom. Around 75% of accepted power is radiated by the multiport wire antenna, but the overall efficiency is less than the multiport wire antenna because of additional loss of power divider power. And we published this prototype in AWPL and also presented in IMS 2024. In this table, you can see a comparison between a multiport wire antenna and phase array. As you can see, both provide lossless power combining from different ports. Also, they both provide beamforming. However, mutual coupling still remains a problem in phase array, but in multiport antenna, it not only is not a problem, but also is beneficial for do beamforming. And also, phase array antenna are usually narrowband, while the multiport antenna can be wide. Next, I will discuss the adaptive RF filtering capability of multiport wire antenna. With increased demand for high-speed communication, systems usually require wider bandwidth. However, some applications just use a small portion of this bandwidth. On the other hand, limited available space in wireless communication systems forces us to integrate different components like antenna and filter all into one component. That was the reason for the emerging of filtering antenna. But filtering antenna suffer from flexibility to adjust the frequency response. And this was for motivation to use a multiport antenna to also do RF filtering additional to the configurable radiation. You can see here the core concept of RF filtering that is based on adjusting the gain of whole of the system by tuning the mismatch between multiport antenna and power combiner. To analyze the multiport wire antenna, we first start with calculating the input impedances using the impedance matrix of multiport wire antenna phase of each port. And then we calculate the received power spectrum using this equation. That gamma I is the reflection coefficient from each port. This flowchart illustrates the steps of systematic design procedure, and this one is quite similar to what we had in the last project, but this time we optimize the power spectrum function instead of radiation pattern function. Next, I'll show the result for the same protocol. As you can see here in this plot, the normalized gain for 3 different optimizations but with different targets at different frequencies that's shown here. There is 2 dB bandwidth for each curve and also around 5 dB rejection between center to center of 2 adjacent channels. And also, as you can see, there is a 10 dB gain difference at 14 GHz for just by adjusting the phase of each port. And this 10 dB gain difference also is obvious in radiation pattern, simulated radiation pattern as well. That verifies the idea of RF filtering by multiport wire antenna. Further demonstrate the versatility of multiport wire antenna, we did optimization with 2 different targets as well, like increasing the bandwidth in comparison to this one, and also 2-band operation, 2-passband operation as well. In this table, you can see a comparison between filtering antenna and proposed multiport filtering. Both provide RF filtering, but filtering antenna have a steep roll-off due to using high quality factor resonators, but multiport filter can provide adjustable passband and also multi-band operation. And we published this work in AWPL as well, not with microwave. Next, I will discuss the second project is multiport patch antenna to provide 2-dimensional radiation pattern. As you know, patch antennas are widely used in communication systems because of several unique properties. However, traditional patch antenna have certain limitation in terms of flexibility. We added a multiport technique to patch antenna to provide more flexibility, like 2-dimensional radiation pattern. To analyze the multiport patch antenna, we first start with calculating the input and the E-field distribution inside the cavity of patch. And then, based on this equation, when we have all the E-field components inside the cavity, we can calculate the radiation pattern. It is generally known that the radiation of patch antennas originates from the sidewall. Each sidewall can be modeled with a magnetic dipole. For example, for the first slot alongside the x-axis, magnetic dipole can be calculated like this, and then based on this magnetic dipole, we can calculate the far field components. Similarly, we can calculate the E-field component, far field radiation from the second slot of radiation pattern. And we follow the same process for slots from, alongside the y-axis, the first one and second one. And then now we have all the radiation pattern component, and by combining them we can calculate the radiation pattern. Similar to our previous work, we use the Calculus model as well to calculate the impedance matrix of multiport wire and multiport patch antenna. And next I'll discuss the design example. In this example, the goal is to determine the location and excitation of each port in multiport patch antenna to provide a radiation pattern with this beam width at 28 gigahertz with this beam direction. Based on this beam width, we determine the dimension of the patch antenna like this. And here, you can see the analytical results for each iteration of optimization process. As you can see, when the number of ports increase, the mean square error metric decrease, and also the analytical result give us the radiation pattern exactly alongside the target beam direction, and also simulation results completely are matched with analytical results. Here you can see a comparison between the impedance matrix for different elements in impedance matrix of the 4-port antenna. As you can see, there is a good agreement between the simulation results and analytical results, and based on this prediction, we designed a practical 4-port patch antenna, and you can see here that each port is well matched. In this table, you can see the comparison between multiport patch antenna and normalized patch antenna, normal patch antenna. As you can see, the multiport idea can add more flexibility to normal patch antenna, and we published this work in AWPL as well. Third project, I'm focused on configurable 2-dimensional multiport periodic antenna. In our last project, we were focused on accurate analytical studies of radiators. However, it is not always possible to provide analytical study on a structure because sometimes antenna structures are too complicated to study. In this project, we introduced a novel theory based on a prediction of the radiation characteristic using the S matrix of the antenna. It means we explore a range of multiport antennas that are built based on the traveling wave concept. Traveling wave antenna radiate electromagnetic energy gradually as the wave propagates within the guiding wave structure. Recently, it has been shown that the periodic structure can realize a closed bandgap at a center frequency using mode degeneracy. As a result, for this linear behavior in dispersion diagram, that we have a non-zero group delay at center frequency, then it can guarantee the process radiation pattern. So that was the reason we were focused on applying multiport idea onto the periodic structure, as they can radiate from backward to forward and from both sides without any problem. Next, I discuss the concept of 2D case. This figure depicts the 2D structure, which is constructed from 2D grade of transmission line that intersect at the junction point. In this case, to simplify the analysis, we consider the unit cell that have similar characteristics between two directions. I mean, for example, the impedance and the characteristic impedance of transmission line in X direction and Y direction is same. Also, we consider we treat this unit cell just as a 4-port network, and we use just its S matrix. And we have no idea about the physical shape of the antenna in all of the design process. Also, we consider 4 ports around the unit cell at the boundaries of the unit cell that inject power into the antenna. So we have 2 different pair of ports. One pair alongside the x-axis and one pair alongside the y-axis. We assume that each port just generates 2 different traveling waves alongside its branches. And similarly, we have the same for ports located in Y branch. On the other port, we're neglecting any traveling wave in the side branch. Later, I'll show some simulation result that verifies this assumption. Based on this assumption, we calculate the E-field distribution between two successive poles, I mean in a subsection, each subsection, using this equation. That all these parameters obtained from the S parameters. And finally, the E-field distribution in entire X branch and obtained from this equation. Similarly, we use the same equation to obtain the E-field distribution alongside the y-axis as well. Now we have all the E-field distribution in 2D gray. Now we use the same E-fields to calculate the radiation pattern. For example, for each aperture alongside the x-axis, the magnetic dipole can calculate like this, and then E-field far field component can calculate from this equation. And we have the radiation pattern from each aperture alongside the x-axis from that equation. We calculate the same for each aperture alongside the y-axis as well. And next, to calculate the total radiation pattern, we use superposition by breaking down the 2D case into 1D case. That includes 10 aperture alongside the x-axis and 10 aperture alongside the y-axis that are arranged in two one-dimensional array. And finally, by combination of all the fields, we can calculate the total radiation pattern. And we published this analytical study in Transactional Antenna Propagation. Similar to previous work, we need the impedance matrix of this structure as well to determine the port excitation. The blue area refers to the ports alongside the x-axis, and the red area refers to the ports alongside the y-axis. And the gray area related to the coupling between ports alongside the y-axis and x-axis. That in this work we approximate to be 0. The main diagonal elements are equal to block impedance, and for those ports are located in different branch, the coupling is around 0, but for those ports are located in the same branch, the coupling between them can calculate it from this equation, which alpha b is the attenuation constant, block attenuation constant, and dij is the physical distance between two ports. Next, I show the prototype structure. You can see here the unit cell, which is based on a planar waveguide. There are 3 types of slots on the top metal layer to radiate, and the overall structure of multiport antenna is shown here, that arranged in a 5 by 5 array, and all the side walls are terminated to match loop to avoid any reflection back from the sides. And also there are 12 ports, 6 alongside the x-axis and 6 alongside the y-axis to excite the antenna. The eigenmode mode simulation shows that 3 degenerated eigenmode mode at the center frequency. The second and third modes are pretty similar, and both are odd mode, and they have the similar resonance frequency. But the first mode is even mode, and usually there is a band gap between this one and 2 others. If we design the unit cell correctly, we can degenerate this one with 2 others and close the band gap at the center frequency. This is a dispersion diagram of unit cell. Here we can see the magnitude of E fields in 2D case when we excite only one port alongside the x-axis and one port alongside the y-axis. As you can see, only the corresponding branch is excited, and the other branch are and here there is a comparison between impedances of impedance matrix. This one shows a real part and imaginary part of Z11, which is an example of impedance of self-impedance, and this one is an example of coupling between 2 ports that are located in the same branch, and these are the coupling between ports are located in different branches, and we correctly consider them around 0. Here you can see the feeding networks of antenna that include a power divider network, some phase shifter, and also each microstrip line connected to the antenna using a microstrip taper and the microstrip to CPW transition. In the next step, I discussed the measurement result for prototype. Finally, we fabricated this antenna and measured, as you can see in this picture.
What is the physical size?
What?
What is the physical size of that?
It's around 21 centimeter to 21 centimeter approximately. This figure illustrates the comparison between reflection coefficient from input port that show the antenna is well matched in both frequency bandwidths around the center frequency with the capability of multi-port periodic antenna to.
I think this is a better plot because it's not dB. Again.
Yes, this is the normalized value for radiation pattern in both direction, E plane and H plane. That it's obvious that antenna can provide around 90-degree beam scan from backward to forward in both directions. And this figure shows the measured result for radiation pattern at center frequency that obtained with two different beam widths.
And what is the center frequency? What is your frequency?
7 gigahertz. It's the center frequency, 7 gigahertz. And also this figure demonstrates the ability of focus antenna in producing arbitrary patterns with multiple beams in different directions. That each of beam in multi-beam can optimize with different beam widths and different direction independently. And this table shows the operation of antenna in different frequencies. As you can see, the best operation is obtained for the center frequency with efficiency of 47%, 9 dB gain, and minus 8 dB cycle level. But as we moving away from the center frequency, we see there is a decline in operation, but it's still acceptable. And we published this work in AWPR. As a conclusion for this work, we presented some systematic approaches to design different multi-port antennas, and we present configurable apertures based on an abstract modeling of multi-port antennas. By reducing the EM simulations, this work offers a practical means to develop future configurable radiators. And here is a list of publications we had during the PhD program. And thank you for your attention.
Okay, we can take one question from the audience if you guys have any before we let you go. Very good.